So, and this morning, first speaker is Marija Jelic Milutinovic from Belgrade, and she's going to talk about simplicial complexes from graphs.
Okay, you hear me, right? Yeah, that's good. Well, first, I'd like to thank to the organizers for inviting me. I'm really glad to be here. My title is Simplicial Complexes from Graphs, and my idea is to talk about it in a really simple and I would say relaxing way. It's morning, right? So there are many combinatorial techniques, algebraic techniques that we applied here. But what I would like to do is just to emphasize some old and new ideas and results, some general, feeling there. And well, see how do you feel about it. Okay, so this is some kind of outline of the talk. I'm just going to move this share. Well, at first, I'm going to revisit a bit simplicial complexes. Maybe there are just some students who are not so familiar with combinatorial approach. Then I'm going to talk a little bit about history and some important classes of simplicial complexes. And then I'm going to mention brief reachability because it's kind of very important here. And then I'm going to go to some original results. I'm going to go talk about cut complexes. It's based on these papers, preprint. And it's joint work with Mark, Marge, Sheila, Rowan, and Leigh. All of them are from United States. So cut complexes are new graph complexes. We define them. And then I'm going to talk a little bit about matching complexes and perfect matching complexes. Well, matching complexes are all graph complexes. We know a lot about them. So I'm going to mention some new results. And again, it's based on joint work with Margaret and Julie from United States. Okay, let me start. Well, simplicial complex, we are used so much to that. We have that geometric approach. We build a nice structure from these nice building blocks. Okay, so simplest is a convex hull of independent points. And then we glue them in a nice way, right? We glue them so that intersection is again a simplex. And we know that we have combinatorial approach, right? We have abstract simplicial complex, which is just a family of sets that is closed under taking subsets. And we have this nice correspondence. Of course, geometric simplicial complex, like this one, has its underlying abstract simplicial complex, and vice versa. For every abstract simplicial complex, we have a geometric realization, and all of them are topologically equivalent. And what we use all the time is dimension. It's just geometric dimension that we see. And we will need this notion of a facet. That's a maximal simplex. So what we can do is we can define every simplicial complex by just set of its facets. So maximal simplices. And we're going to do it a lot. And I need this notion of pure simplicial complex. That is simplicial complex whose all facets have the same dimension. So not this one, or either all triangles or all edges or K complexes. Okay, enough about basic things. So what are graph complexes? Very basic idea would be to have a graph and then construct a simplicial complex in some way. And I stated here some well-known graph complexes. I made a little difference here, you see. So first three, neighborhood complex, independence complex, and clique complex, they are constructed such that their vertex set is just vertex set of the graph. Like you just have the graph, you forget about edges for a moment, and on those vertices, you construct simplices in some way. Well, then we have this exotic box complex, whose vertex set is kind of rare. We have two copies of vertex sets of graph. And then we have these three whose vertex set is actually edge set of the graph. We are going to talk a bit about them. And we have many more. We have this Jakob Jonsson, that's actually doctoral dissertation. And there are more than 18 simplicial complexes from graphs. It's a really nice reference for anyone who wants to see where do we apply them, why do we construct them, like all the intuition and history. Well, unfortunately, when I wanted to try to contact Jakob Jonsson, because I know he's an expert, I went to his webpage and it says, I left academia. I'm not reachable this email anymore. And that's the yeah. Okay, I'm going to mention clique complex, well, just to get a general feeling. This is our graph. And as I said, the vertex set of our complex is going to be just vertex set of this graph. And what do we do? Whenever we have, for example, this triangle we have, so we have full subcomplex, complete subcomplex, we're going to put a simplex there, and also we have these K4, right? We're going to put a tetrahedron here. So these things, and when we do all of those things, we get Knight complex. And these complexes, they are very important, for example, in persistent homology and those things. They use them a lot. And now I'm going to talk a little bit about history, about this beautiful result. I think I definitely want to mention it because that's the kind of birth of topological combinatorics. And this emphasized the idea that we have a lot in topological combinatorics. So we have some completely combinatorial statement or some statement that comes from completely different field, okay? And then we prove it by using topology. And it turns out that maybe there is no other proof than some proof from topology. So let's see what's that. So Kneser, he conjectured something like this. We have some n set, and we have all k sets of that n set, okay? And what he said, well, it's like an easy exercise. You can partition all those k subsets into n minus 2k plus 2 classes. Like I have some k subsets, blah, 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 some k subsets, okay? And I know I can do it in such a way that in every class, there are no disjoint k subsets. So no disjoint, no disjoint. All of them have, each two of them have some intersection. And it's very simple, like it's high school problem. And he asked, can we do it just with one last class? And it turned out to be extremely complicated problem. It was solved more than 20 years later by Laszlo Lovász. He got a Nobel Prize a few years ago. And I don't know why it was open for so long time. My guess is that maybe people just try to do it by some standard algebraic, combinatorial techniques, and they have never had any other approach. And Laszlo did it in an amazing way, which is just always appearing in topological combinatorics proofs. So what did he do? At first, there is some graph that translates the problem. So what is Kneser graph? K, Kg, and K. So for example, let's say that our n is 5, our k is 2. So we are looking at two subsets of a 5 set, okay, like 2, 3, blah, blah, all of these vertices. And we say the two vertices in this graph are connected if and only if they are disjoint, okay? And what I get here is Peterson graph. And how do we translate this conjecture now? Well, we know that the answer here, since Laszlo Lovász said, is no, so I'm going to translate it in this way. It says something about chromatic number of this graph, right? Because we can think about this. Let's say that one class up there is just a color, okay? So what do I want to do? I want to color this graph in such a way that in the same color, we don't have this joint subset. So in the same color, I don't have two vertices that are connected. So I'm talking exactly about chromatic number of this graph, right? And what actually we want to prove is that chromatic number of this graph is n minus 2k plus 2. Okay, so let's just illustrate these beautiful proof ideas. First thing Laszlo Lovász did, and it was really new, he constructed a graph complex. And its neighborhood complex n of g. So how do we construct it? The vertex set of, n of g for any graph g is just the vertex set of g. Okay, we keep same vertices. And how do we put faces? Whenever some set of vertices, as it's written here, has a common neighbor, we put a simplex there. So we can think in another direction. What are the facets? Well, we choose vertex, we look at the set of all its neighbors, and we put a simplex there, and that's a facet. Okay. Not that's one vertex, only the neighbors. It's like open neighborhood. And then what he proved is this well, beautiful transition that if this neighborhood complex is topologically unconnected, like its homotopy groups vanish up to some dimension, then graph G is not M+2 colorable. And here is this topological part. He used the Borsuk-Ulam theorem. Well, not Borsuk-Ulam theorem, well, as we usually think of it, that statement with covering of spheres with closed sets. And the last part, of course, would be to prove that this is indeed n-2k-1 connected. He proved it by induction, like constructing the complex in some steps. So this is like very common idea in topological combinatorics, that we have some, configuration space, and then we translate our problem into some topological property of our configuration space. And graph complexes are very often configuration spaces or their joins or things like that. Okay, now I'm going further to this shellability property. If some of you live in more algebraic world and not talk much about shellability. So what is shellability? Well, we build simplicial complexes somehow, but we want to see if we can build them in a really nice way. How? Well, again, we want those building blocks to fit nicely, and our building blocks are going to be facets. So just maximal simplices. And here is precise definition. It says that, well, let's have an ordering of facets. Facet, 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 facet. When that ordering is a shelling. It's a shelling if for every facet, when we look at its intersection with the union of previous building blocks, what we already built, that intersection is pure codimension 1. Okay? And then it's a shelling order. If some simplicial complex has shelling order, at least one, we call it shellable. Okay, let's take a look at an example. For example, triangulated triangle is shellable. We put triangle, we put another triangle. Intersection is codimension 1, right? It's just edge. We put third, again, codimension 1, nice. And we can go for tetrahedron 1, 2, 3, and put fourth, again, nice. They're shellable. And there's a general statement. It was proved, it's a nice result, that boundary complex of a polytope is always shellable. Okay, so why do I mentioning it now? Okay, let's see. Non-shellable complex. We could try like 1, 2. It's okay. Everything is okay. And then we put this, and it's not shellable. Well, it's not shelling. Of course, this is not proof that there is no shelling. But we have a proof, very nice theorem. How do we think here? Well, this is pure complex of dimension 2, but it is homotopy equivalent to S1, so it's not shellable. Björner proved that. He proved that a pure shellable complex of dimension D is always either contractible or homotopy equivalent to a wedge of spheres of dimension D. So whenever we have homotopy type, we can say something maybe about not being shellable. Okay, now I'm going to these new complexes. So maybe this is a good time to, well, you don't have questions. All of this is like waking up, right? Okay, cut complexes. Let's define them. Okay, I have a graph, and this is just a notion for a subgraph. And I'm going to need these two terms, like, well, disconnected k-sets is just disconnected, and I'm going to need this to call them somehow. The rest, well, I have some disconnected part, and the rest I'm going to call it separating part, because when I remove it, the rest is disconnected. For example, here, this red set is separating set because the remaining part is disconnected now. Okay, so my k-cut complex for some k, at least 2, is simplicial complex whose facets are the separating sets of size n minus k. Well, let's see an example just to get used to that. For example, I have this C5 cycle. I want to find 2-cut complex. So I'm going to look at n minus 2 separating sets. So everything, all sets of vertices, such that when I remove them, the rest is disconnected. For example, this red is separating, so I put the triangle there. Again, 1, 2, 4 is separating set, so I put it there, and go on. Blah, blah, blah. Yeah, I got it. This is my 2-cut complex. It's Mobius band, and it's not shellable. And we're going to know much stronger statement later. Okay, why do we do it? Like, why did we define these complexes? I drew this picture because I like to think about, mathematical disciplines as very good friends. I think I'm missing topology here, definitely, or I could say that they live in the world of topology. So first I need a notion of chordal graph. So chordal graph is graph that has no induced cycle of size greater than 3. For example, C5, it has induced cycle length 5, so it's not chordal. And Froberg, a long time ago, he proved this more algebraic statement. He said that a Stanley-Reisner ideal generated by quadratic square field monomials has a linear resolution if and only if this delta is the Lie complex of a chordal graph. Okay, so, well, it's proved that the Stanley-Reisner ideal, I delta is generated by quadratic square field monomials if and only if delta is Lie complex. So this part with linear resolution, that comes with chordal graphs. So just to like maybe clarify that a little. We didn't work with that one. That was like basic theorem. Most of my collaborators are from combinatorics. But there is a very nice translation of this theorem. You see, it's very different from previous one. Egon and Reiner translated it. And they say that actually what it says is that graph is chordal if and only if this delta 2 is shallow, and that it happens if and only if this delta 2 is vertex decomposable. Okay, I didn't mention vertex decomposability because I'm not going to work with that much. It's that inductive construction. It's stronger than shellability, and maybe I can say something if someone is interested. Okay, so what was our idea is to extend Egon-Reiner theorem, because actually Egon and Reiner, they didn't call this delta 2. They had this complex. And what we did, we generated that for delta k to see what happens when we not look just at, complements of disconnected 2 sets, but complements of disconnected k sets. See if we can somehow say that when is delta k of G shallow? Okay. And in general, to relate topological properties of this delta k to graph properties of G. Okay, so let's talk a little bit about our project. Well, first thing, we wanted to, see some natural properties of our construction. There is this simple proposition that says that, okay, if delta k of G is shallow, for all of its subgraphs, we have also shallow cut complex. And then we should think about another direction. Somehow, can we look at, shallowability of parts and just glue them together and get a huge shallow complex? And these constructions are natural. Disjoint union, join, and wedge product. So let's see how graphs behave according to them. Okay, first disjoint union. That would help us at least to, look at connected components. And it behaves nicely. It says that this delta k of disjoint union of graphs is shallowable if and only if both parts are shallowable, like very natural thing. Okay, that's very simple. And this is like a messy construction. We construct join of two graphs. I don't know how common is that notion in graph theory, but actually you can see when you try a little bit that you can build many graphs by using join and disjoint union. It's just, we have two graphs like this part 1, 2, 3, 4 and the rest part, and then we connect every vertex from this part to every vertex from the other part. And how does this behave? Well, we prove that delta k of join is shallowable if and only if one of them is void, has no faces, and the other is shallowable. Well, void, it's not something we would think of at first. But for example, cut complex of complete graph is void, right? Whatever you take out, nothing is going to be disconnected. So they appear actually. And so when you have join of, for example, complete graph as something else, for which we know that cut complex is shallowable, that is again going to be shallowable. So yeah, it says a lot. And well, it looks like a simple statement, but combinatorial party stuff, like talking about proofs here would be, hard. And of course, we have this, consequence actually, that whenever we have just one added vertex, like a vertex that is connected to all vertices we had before, that cut complex is shallowable if and only if the complex we started with was shallowable. And the third construction, well, this is something that allows us to work with those graphs that have like a disconnecting point, disconnecting vertex. It says, okay, what can we do about wedge product of two graphs? Like we have graph, and we just identify two vertices. And again, we have this result that cut complex of this wedge product is shellable if and only if both parts are shellable. So it's nice, like you can add graphs and keep shellability. And now we can finally have some, results for general classes of graphs. First, threshold graphs. Those are graphs that can be constructed from a single vertex, such that in each step you either add an isolated vertex or a dominating vertex. So add something isolated or connect to all that is there. And when we think a little bit, it's easy to see that whenever we have a threshold graph, delta k of g is shellable because of the previous constructions. And of course, trees, they can be seen as wedge product, right? So their cut complexes are always shellable. And now there is this nice theorem, which is a bit harder, and it says that whenever graph is chordal, then its three cut complex is shellable. So it's a kind of extension of that Froberg's result. Unfortunately, that does not hold for higher k. We've constructed some chordal graphs for which this complex is not shellable. Okay, well, now a bunch of results like bipartite, multipartite, cycle, and so on. Here is this table. Someone can read results in the paper. But one idea that, is here more general than just these results is to use that property that if graph has shellable complex, then all of its subgraphs also have shellable cut complexes. Okay, so for example, if we have something, for example, some bipartite graph that doesn't have shellable complex, and if that is induced subgraph of our graph, we know that that part is like obstruction to shellability, and entire cut complex is not going to be shellable. And one of our questions that we work on is to find those obstructions to shellability, like minimal set of obstructions to shellability. Like, we know obstruction to planarity, like we know just two of them, and just to reduce the number of them. Okay, what were our tools? We use discrete Morse theory a lot, like large combinatorial proofs. Well, I say algebraic topology. It's like homology and things like that. Of course, homotopy types and those like constructions and properties. And we use Pisa topology. It's very nice here to go into completely combinatorial part and read something there in the phase lattice. And this is too much for a slide by all rules of slides, but this theorem is so huge. I just wanted to state it to just, give the idea what happens. So what is this? We go to poset, world. We say, okay, we have our graph. It's some graph on vertex set of size n. And we take truncated Boolean lattice of subsets of sample size at most n minus k. So what's that? That's what we have, right? We have n minus k sets here. And well, we have some notion, some zk notion. And then we have this huge theorem, which actually says something like that. If we can, by looking at the phase lattice, observe some nice properties, for example, this thing, that phase poset coincides with this thing. Like we see phase poset. All of these statements are, just that combinatorics there. If any of those parts holds, we can compute reduced Euler characteristic, which is nice, right? And if we have any of these combinatorial things in the poset, here, if we also know that it is shellable, we actually know what is the homotopy type. And also here, for example, without shellability, we can say that, for example, our cut complex is torsion-free and that homology occurs in at most 2 dimensions. So things like that, just the flavor of poset topology. Okay, there is also another complex that we also worked on, because you remember when I started, when we had our motivation, we started from delta 2. So we wanted to take out n minus 2 vertices such that those 2 points remain disconnected, right? And we generalized that k vertices remain disconnected. But those 2 points were not just disconnected, they were completely independent. Like 2 points not connected are always independent. So it's natural to take a look at that construction too. So I want stronger thing, not to leave k disconnected part, but completely independent part. And that is what we called total k complex. So the facets there are complements of independent sets of size k. And of course, this total cut complex is always just subcomplex of what we started with. For k equals 2, they're coincide. And they're similar results, similar ideas. And we prove this generalization. It is kind of generalization of that Egon-Reiner theorem. It says that this total cut complex is vertex decomposable for all k at least 2, if and only if it is shellable also, and if and only if G is the chordal graph. So we have this generalization of Froberg's result. Maybe, yeah. Now we can say something about questions. Well, at first thing that I already mentioned is that what is the obstruction to shellability? Like, can we define the minimal set of graphs such that, if our cut complex is not shellable for some k, well, it definitely has a subgraph that is something like bipartite and things like that. We would like to know that. Please let me know if you find out. And also, we would like to fully extend the Froberg-Egon-Reiner theorem to say, well, we exactly know when is it shellable, if and only if G is something, maybe not only chordal, maybe something else we are missing there. And that's it about this part of results. We're now going to talk about much more familiar graphs, matching complexes and matching complexes. Okay, this is joint work with Margaret and Julie. And I'm going to start with, again, some introduction for those who are not familiar with the graph complexes. We need notion of a matching of a graph. What's that? There's just set of independent, pairwise independent edges, like this red set. If we look at this red set, each 2 edges here are not adjacent. Okay? And how do we construct matching complex? Well, let's look at this graph. For each edge, we put a vertex there. So you see, I put them nicely so that matching complex is nice. And okay, whenever we have a matching, we put simplex. For example, these 3 edges, they correspond to this triangle. Okay? And well, we need to mention that matching complexes are actually just a special part of independence complexes, but a huge special part. Independence complex is complex I mentioned in the beginning. So I have vertices and I put simplex whenever I have independent set of vertices, like contrary to what I did in cut complexes, but they are not related. People usually ask if they are related because it's like independent sets, and those are like complements of independent sets. They are not Alexander duals. They are not, you cannot see one from another. And well, if I have graph G and I go to matching complex, I have it directly, or I can go to line graph of G and then go to its independence complex, and I'm going to get the same. For example, nice thing is that when I have bipartite graph, its matching complex is just torus. And what do we know about them? Again, too much on one slide. These complexes come from algebraic world. For example, this complex, it appeared in relation to those groups and M of Kn. And there are so many things, where you can see this matching complex. There are various connections to representation theory, but this thing is interesting. We still don't know much about topology. It is still very mysterious. So it looks simple, like you have complete graph, you could understand something there, but you don't. like it's fully known only for n at most 12. There are some, discrete results later. We see torsion. For example, we see that M of K7 has Z3 as its first homology group, but we don't see much otherwise. It's very, very similar for M of complete bipartite graph. I like this result about connectivity of that complex. And it's nice that it is also chessboard complex. That's the same thing. Those complexes appeared in Tverbreck type results and things like that. And they have many applications. Nice reference again is this survey by Michel Wax. You can see so many things about them there, maybe connections to representation theory and so on. Okay, what do we know apart from that we don't know for bipartite and complete graphs? We know just for some simple classes like paths, cycles, forests, so some linear structure. And we know some small things about grid graphs and polygonal line tilings. What is a polygonal line tiling? Well, you have some n, and you put n-gons one next to another. And that's what we know. And we asked, well, a few years ago, we asked a reverse question. If we wanted to see, okay, we know that everything can be independence complex. So what can be matching complex? For example, which combinatorial manifolds are matching complexes? And we gave complete answers, so we know now which combinatorial manifolds with or without boundary are matching complexes. Okay, but that's not topic. So things that we wanted to do is somehow to generalize, like to see what else has a nice matching complex. And first, freedom we gave us is not to glue just same polygons, but to glue arbitrary polygons. Then it's not so nice anymore. The structure is not so nice. And for example, this is some kind of extending polynomial line tiling. So I have quadrilateral, hexagon. I could have anything here, but it was harder to draw a picture. And then I also have some, tails. Tails don't change much. And what we proved is that whenever we have line of any polygons, the matching complex is either contractible or homotopy equivalent to a wedge of spheres. And well, we should mention Fibonacci in Pisa, right? This is nice representation. When we have line of pentagons, the homotopy type is directly connected to Fibonacci numbers. Just a cute result. And well, what is the next step? Like, can we, make our set of nice matching complexes bigger? And the next thing would be outer planar graphs. So graph is outer planar if you can draw it such that all of its vertices lie on an huge unbounded face. And maybe it looks just like polygons, but it's actually not. Well, both of these things are outer planar, and also if you take wedge of them or wedge of several copies, you again have an outer planar graph. So it's much smaller than planar graphs, but still huge class of graphs. And we proved that, as we would expect, we expected that their matching complexes are either contractible or homotopy equivalent to a wedge of spheres, which is nice. You see the structure. And which kind of tools we used? Well, it's natural, and we were surprised that people didn't prove it, although there are, many details. We somehow collected very sparse constructions from independent complexes, and we translated them. For some of them, it was easy to translate them. For one on the next page, maybe not too obvious. So, for example, something like that. If I have triangle, I have an edge whose neighborhood is inside of the neighborhood of another edge, and maybe I should use that in the matching complex. So, like I go to combinatorics, and somehow I see that I can collapse things there. And what this theorem says is something like this, that if graph contains two edges such that open neighborhood of one edge is contained in open neighborhood of another, then I have just same homotopy type if I remove that edge. And same with the closed neighborhood, just it's a little bit bigger expression. I know that I can remove the edge, and I also have the part when I remove entire closed neighborhood. And the next thing we need is this thing. When I have polygons, I would like to somehow reduce them. And then again, it says that if I have a path of length 4, whose internal vertices are of degree 2, so like an induced path of length 4, I can again just collapse it and have nice, how to say, transformation in the matching complex. So all of these reduction, I stated papers to see that they come from different parts. They gave us the result. And of course, we used the combinatorial properties of outer planar graphs. For example, this one, that biconnected outer planar graphs. So those that don't have those tails and a little bit stronger, they can be presented as with basic cycles, and that we have that nice presentation such that basic cycle we can actually go around with them. So these are things that we expected by looking at matching complexes for a long time. And we have these questions. For example, okay, maybe not linear structure or this outer planar, but something that is definitely not outer planar, but nice. What can we say about matching complexes for honeycomb graphs? Matching complexes of honeycomb graphs, they appeared because matchings of outer planar graphs, honeycomb graphs are really interesting. So that would be something next that is not so, I don't say how to say, not linear, but simpler. And this is a question that I really like. So which graph properties give torsion in the matching complex? So what is the thing that you have in your graph that induces that torsion? Because we see that these nice and simple things, they definitely don't have torsion. But for example, K7, its matching complex has torsion. Or for example, I would say, I think it's 5,5. Its matching complex also has torsion. So there is something about the graph that induces torsion in the matching complex. And we were free to make this conjecture because we don't see any planar graph which has torsion. We believe that matching complex for every planar graph is contractible or homotopy equivalent to edge of spheres. So if you prove or disprove it, let me know. Okay, so the next thing I wanted to talk about are perfect matching complexes. As you can see, matching complexes can be really complicated. And people worked on them a lot and they couldn't see much. And we try to look at a sum complex that is really nice. Well, what is perfect matching complex? First, we need perfect matching. Well, it's matching that covers all the vertices. So matching is perfect matching if all the vertices are covered. For example, if we have odd number of vertices, there is no perfect matching, nothing. And what is perfect matching complex? Well, denoted by now a little bit different notion. It's, again, its set of vertices is sets of edges of G, and facets, they correspond to perfect matchings of G. So I guess you remember the picture we started with when we talked about matching complexes. So now I have just facets based on perfect matching. So these three give this triangle, and we miss those edges. See? So it is definitely subcomplex of the matching complex. Okay, these are some simple statements. Well, if G admits at least one perfect matching, then we have full dimensional subcomplex. And well, if there is no perfect matching, then we have just a discrete set. And perfect matching complex coincides often with, well, not so often, with matching complex. For example, for K complete graph on even number of vertices, perfect matching and matching complex are same. So again, we have complicated situation. And of course, when we have K and N, same number of vertices, we have the same complex. But for example, for cycles, it's really nothing. Okay, so again, it turns out that it's hard to work with them. So we choose to try with these honeycombs, like this not simplest, but from my perspective, the nicest structure among those that are completely untouchable from the perspective of matching complexes. And well, we should have some notion how to define honeycomb graphs. I have these honeycombs, and I want to look at those that have these, you see that these hexagonal edges. This is like 2 by 4 by 3 honeycomb. Okay? I don't put precise definition. I think it's okay. Just to, see the idea. And we don't know much about their matching complex. We have just some connectivity bounds. Okay, so what can we say about the homotopy type of this perfect matching complex? And first thing, it's like without some another perspective, we couldn't say anything. But then we looked at this completely different thing. And this is so beautiful. I'm always amazed with this relation between, completely different objects. When you have one object and something completely different somewhere else, and you see that those like same things just in different language. And this is one of those situations. Like, what is plane partition? First, look at this as, object in plane. What do I have here? Just some rhombus in the plane. And you can continue putting rhombus in some way. So you can put in this, or this direction. Okay, and you can continue go on. So that's a plane partition. It has its definition, but just imagine putting rhombus in this, nice way, nice glowing. But another way to look at it is to say, okay, what if this is in 3D? So if we look at this as piles of unit cubes, so and now I put this black thing for tops, and do you see now three-dimensional object? I have one cube, I have some wall, okay? I have 0 cubes, I have 2 cubes, I have some wall, okay? And I have 3 cubes. So now it becomes just, some structure in 3D. And I can code it with this number, okay? And you can believe me that whenever I have this code, I can easily draw this. Like this plane partition, it's uniquely defined. You can't do it in any other way. Okay, so in general, if I have plane partition with more entries, that's always like some k times n matrix whose entries goes up to this n. So you can imagine bigger thing. Just the picture is not so simple to be drawn now. So why am I talking about this? Okay, now look at these edges. Well, when I have these top parts, I put these red edges, okay, in this parallel to some axis. Okay, and for these white parts, I put these green edges parallel to the bottom part. Okay, I'm doing something. Why? Because when you just look at it, see, I have a perfect matching of a honeycomb graph. And that's so cool, right? You read from here a perfect matching of a honeycomb graph. And that result has never been stated like clearly. You have to read the papers that are more so combinatorial that, they talk and talk and talk about the nice structures. Those papers, they talk much and they don't give like precise definitions and things like that, but that is so beautiful. Okay, so what we have now is that every perfect matching has this code. And it was really hard to work with perfect matchings before, but now with these codes, with these just 4 places, we know everything. It's much simpler. Like some, when you go to algebra and you get some ring and you solve problem there and then you go back. It's that kind of thing. So to be precise, whenever I put these red parts, everything else is defined. And now we could prove things, finally, by looking at this completely different structure. We proved that, for example, when we have really simple case, h1 times 1 times 1 times n, we have a contractible perfect matching complex. Then for 1 times 2 times n, we have a sphere. And when we have 1 times m times n, we again have contractible when m and n are at least 3. And for 2 by 2 by 2, we have wedge of 2 as 3 spheres. And here we used discrete Morse theory. But we didn't look at perfect. We look at these, codes, and essentially we did things there. Yeah, and that's some acknowledgements. That's basically all I wanted to say. So we have plenty of time for questions. So thank you.
Thank you very much. Any questions?
I did not understand how the honeycomb matching and the rhombus plane division are related.
Okay, so those, as I said, those are kind of old results that are usually combinatorially stated. So I have, let me go back here. So whenever you have this kind of rhombus tailing, and you just have, like, that's a very strict rule, I didn't state it here. Like, you imagine that it is in plane, so you have x and y axis, and in each of the rhombus, you construct an edge based of its orientation. Okay, so for these that are of this shape, you construct these horizontal edges, and for the others, you construct here, you see, these are actually inclined. Okay, and when you look only at these horizontal edges and look at the others, for example, for every point here, you have we have 3 rhombus, and you can fill the rest and get a hexagon. And now you know that you choose these 3 edges of that hexagon in that perfect matching. Okay, and it turns out that when you go on and on, everything will be, so everything will give you perfect matching. So you will not have a situation that you, for example, have an edge and you choose another edge that has intersection point. You can prove it. I mean, I didn't prove it. It was like all the result that you will cover all the vertices, but not any vertex twice or more. So it comes from, that plane partition combinatorics. It's not something we proved. I'm sorry if I didn't give you the real proof.
Now, asking for the proof, I see the hexagons only in the vertices of that you have all 3 orientations at the same time. But for example, in this picture, I see 1, 2, 3, 4, 5 hexagons. I don't see the entire tiling.
Okay, let's then look at this part. So where would be the problem maybe? For example, you see here, you add hexagons in between also. You see, we have this part that corresponds to this hexagon. Okay, and then maybe you see this hexagon. That's this one. And you see, this part corresponds to those hexagons that actually don't have all 3 edges. See, so these are like connecting parts. And it's very nice that everything fits nicely. So you see, for example, in this hexagon, well, we would expect 3 edges to be chosen, right? But there is just one. And those connecting parts, they fit very well. Those connecting parts are actually going along these, how would I say, the pillars of the construction.
Thanks.
It's good.
More questions?
No, just do you think this is connected just to the dimensions 2 and going from dimension 2 to the dimension 3? Like, do we use planarity in any way, or do we just use that it's a tiling?
Like from we only worked on these that use planarity, but actually I didn't work with it because then you would go to dimension 4 and then maybe things would be less visible. We want it to be more visible. Like this is really I find good intuition here in these, pillars, but I haven't seen any higher dimensional.
Numbers seem to match up, right?
Yeah, I mean numbers do, but here just this intuition of geometrical, piles of cubes. That's something that we wouldn't use.
More questions?
My question goes back to, I guess, cut complexes and that shellability.
Uh-huh.
So it was known for k equals 2 previously, if I got it right. Like this is like a classic result, so to say. And then you also proved k equals 3 And
Okay, so
same way.
just let me find the right point. So Econ and Reiner proved this equivalence for delta 2, for k equals 2.
Yeah.
They didn't call it cut complex. It was actually Alexander dual of something else. Okay, so but it's basically this. And then we proved for k equals 3 one direction for delta, and for delta total we proved equivalence for all k.
So k equals 3 is only one direction.
Yeah.
Yeah. Okay.
And we see that for higher k, we don't have a nice property.
Could you move to that slide with k equals 3? Sorry.
Yeah. So we know this direction, that when graph is chordal, delta 3 is shallow. And well, for higher k, we have chordal graphs with small number of vertices such that delta k is not shallow. So
perfect. Thanks.
Okay. I guess there are no more questions. Or maybe there are. I don't know. No. Okay, then let's thank Marija again. Thank you. I guess we can start. All right, welcome back. Our second talk today. Ran Levi from Aberdeen. He will talk about calculus for modules over posets.
Thank you very much. Thanks to the organizers for inviting me. It's a pleasure to be here. I've been to Pisa in 1984, I think. That's the only time I've been to Pisa before, and it was very nice. But I think I missed a lot of the, like every typical tourist, I only went to see the tilted tower, and that was it. Then proceeded on. So I think there's a lot more to this city to offer. Anyway, so I want to talk about a project that is ongoing. There is already a preprint on arXiv. It's joint work with Jacek Brodsky and Henry Rihimäki. And Rihimäki. And so the motivation for this came from applied topology and topological data analysis. But I'm not going to emphasize that much in this talk. Just tell you that's the motivation. That's where the kind of the drive to do something slightly different from what is normally done came. So I want to start with talking about representation theory. So representation theory in general, representation theory you can understand almost all of, in any kind of representation theory as basically the study of functors from some small category C, let's call it functor M, small category C, to vector spaces over some field K. And the category C can be the category of a group, in which case you're talking about group representation theory. It can be any small category you want. So C, it can be any small category. It can also be something like you can take a directed graph, a digraph, or a quiver, synonymous, and you can look at the path category that it generates, and in fact you can basically represent almost any category, any small category, with not too much topology on objects and morphisms as sort of a quotient category of a path category. So this is a very wide kind of way of looking at representation theory. And what you want to do is to understand functors from that category into vector spaces, okay? And in all of them, there is always the same problem that occurs, and that is, so in all versions, or how about flavors, all flavors of representation theory, you have the same problem. And that is representation type. So what is that? Well, one of the major tasks in any representation theory is to try to classify the intercomposable modules. So basically, there are theorems which tell you what could possibly happen. So the first representation type is what we call discrete. Discrete representation type, which means that the intercomposable modules could be parameterized by some discrete set, okay? Even finite sometimes. So for instance, for a finite group, when you represent over a field whose characteristic is prime to the order of the group, that's the case, okay? Generally, it is not the case, however. Second type is what we call tame representation type. Tame representation type means that you have a finite number of one parameter families that classify all the intercomposables. So finite number of one parameter families. One parameter families of intercomposables. So I did not say that here. I'm talking about K algebraically closed. So for this sort of classification to work, you need that. So algebraically closed in particular is going to be infinite. So finite number of one parameters families of intercomposables means in particular that you're going to have infinitely many of them, but it's still under some control, which is why it's called tame. The third, and unfortunately the most general case, is what is called wild representation type. And that, there are many ways of saying this, which I don't fully understand all of them. But one way to say it is that for every n, you have an n parameter family of intercomposables. For every n, okay? So there's no hope to classify anything. So for every n, there's an n parameter family of intercomposables. Okay. So, as I said, unfortunately, this is the most common case. So, in particular, if you're looking at, if you actually want to apply any of this, for instance, what people do in topological data analysis, they talk about generalized persistence modules, which usually mean, if you want to apply things, usually means you can factor your representation through some finite poset. For most finite posets, for instance, if you take a finite grid on R2, right, with just integer points, and think about that as a poset, right? So if it's like two-dimensional, so AB is less than or equal from BC, if A is less than equal to B, and B is less than or equal to D. So with this sort of order, if you go more than, I think, 4x4 or 5x5, then you're already wild representation type. So it's horrible. Okay, so you can't really use any sort of classification theorem to get any applications done. So what do you do when you have a really complicated situation? Ooh, I'm happy I did my exercise this morning. This is hard. So what do you do when you have a really complicated problem and you want to kind of analyze it? So a very complicated set of objects and you want to analyze them. For instance, what do you do in analysis, in calculus? You have lots of functions and you want to understand them. You're not going to understand them point by point. You're going to actually try to understand them locally. So the approach we have is try to understand modules locally. Like in calculus. So what do you have in calculus? Well, in one-dimensional or multi-dimensional calculus, you have things like the gradient, the divergence, the Laplacian, and so on and so forth. This sort of approach was adapted by graph theories. In applied graph theory in particular, applied graph theory, there is the concept of discrete calculus. Discrete calculus. So, and I want to kind of try to explain this before I do anything else. So this is going to give the motivation, because it's very, very simple. But the way I'm going to do it is not the way it's normally done. I want to do it in a way that will motivate what I'm going to do later, okay? So in particular, I'm going to look at a graph, at a directed graph. So G is a directed graph with vertices V and edges E. So it's the digraph. Okay, and I have, since it's directed, I have two functions which I'm going to call phi and beta for back and for front and back, going from E to V. So phi of an edge E is the front, so the target of E, and beta of E is the back or the source of E. I have these two functions, all right? And now I want to think about functions on the edges and the vertices. So consider functions from E and from V into the integers. Okay? Normally in graph theory, you think about some field like the real numbers, because you want to apply this. So real numbers or the complex numbers, it depends what you want to achieve. But why not the integers? It fits my purposes a little better. Okay? So you have functions like that. So let's look at a set of functions as, in fact, the groups of functions as z to the v and z to the e. Okay, so functions from v to z, functions from e to z. All right. Now, if I have these functions phi and beta from e to v, I get functions the other way. These are abelian groups. These are free abelian groups generated by v and by e. So I have two functions from two homomorphisms, in fact, from z to the v to z to the e, induced by those, by composition, right? And so these are homomorphisms. These are homomorphisms. So what do they do? Just to be sure, if I have a function from v to z, I'm looking at phi star of f of a vertex e. So that is simply f of the target of e, of the front of e. And similarly, beta star of f of e is f of the source of e. And the definition of the gradient for graphs basically is that you're looking at the gradient that goes from z to the v to z to the e is simply nabla is equal to phi star minus beta star. These are abelian groups. The difference of two homomorphisms of abelian groups is again a homomorphism of abelian groups. So here you are with a homomorphism that is defined to be, if I took instead of z, I took r or c. This is exactly the way they do it. They define it in graph theory. And there are many things you can use this for in graph theory, which I'm not going to get into, but because it's so applicable there, in network theory, in lots of other things, this kind of gives a motivation. Why won't you try to do something like that for our problem with modules? Because that is exactly what allows you to study a graph, typically a very large graph, locally. Okay. Right. Okay. So what I'm going to do next is I'm going to do exactly the same thing, but I want to make it a little bit more categorical, because after all, what I'm trying to understand is the category of representations. Okay, so I'm going to categorify this. So what am I going to do? I'm going to look at V and E as discrete categories. Consider V and E as discrete categories. What does that mean? V and E are just sets, so these are the objects, and the only morphisms are the identities. So just discrete categories. Very good. Okay, so now what can I do? I can consider the categories of K, so fix a field. So fix a field, K, and I want to consider KV modules and KE modules. Now, what are these? It's a tiny bit abstract, but really it's nothing complicated. Think about it. A KV module should be a functor from V to vector spaces, to K vector spaces. So for every object, I have a vector space of some dimension, finite, okay? But there are no non-identity morphisms. So really, all that is a function that takes a vertex to a vector space or an edge to a vector space. All right. So these are the KV modules and KE modules, and because I have those two functions from E to V, phi and beta, I get induced functors now, because these are my module categories. So I have induced functors from KV mod. So phi star and beta star to KE mod. And I can define, now I can look at the Grothendieck group of isomorphism classes of KV modules or KE modules. What are those? Look at the isomorphism classes of these modules. What does that mean? It means basically, instead of, I know that any two vector spaces that have the same dimension over the same field are isomorphic to each other. So basically, it's like associating a number. I mean, those Grothendieck group of these modules, isomorphism classes of these modules, are basically the integers, functions from the corresponding set, V or E, to the integers. So the Grothendieck group of KV is isoclasses of KV modules. But all that is really is isomorphic to Z to the V, because if I know that for every vertex in V, I associate some number, that's a vector space of that dimension. Up to isomorphism, that's fine. Okay, so isomorphism classes is just that. And the other one, K to the E, so Grothendieck of KE is just Z to the E, okay? And it's very easy to see that, in fact, phi star and beta star, which I get because I have them on the actual module categories, these two are exactly the same functions I defined before, okay? So I can define now nabla from Grothendieck KV to Grothendieck KE. And well, this is just nabla is nothing but phi star minus beta star as before. Except now I kind of know what to do. I have categorified that kind of situation, and I now can, I use discrete categories. They don't have to be discrete. Representations, after all, are just arbitrary functors from arbitrary small categories into vector spaces. So I can do the same sort of thing, but now I don't have to rely on graphs anymore in this way, on discreteness anymore in this way. Okay, so only finite dimensional vector space. Yes, only finite dimensional vector spaces. I mean, the category doesn't have to be finite, although typically I require it to be finite, but in general, it doesn't have to be finite. I do require, however, that the category has no topology on objects or morphisms. Okay, so for instance, the category of spaces is out. Okay. Okay. So so like I said, this can be done for arbitrary category with these requirements and with certain amounts of success. I want to concentrate on the practically most straightforward example, and that is posets. So restrict to sometimes finite, if I need that, posets. Okay. So one thing I need in a poset is I need to be able to represent it somehow. So the most typical way of representing a poset is by their Hasse diagram. The Hasse diagram of a poset P is nothing but the graph, the digraph, with the same vertices as the objects of P, and with morphisms, which are the indecomposable arrows in P. So the graph, the digraph of indecomposables arrows in P. Right. So going back a little bit to calculus, if you think about the Hasse diagram, you can think about those indecomposable arrows as the minimal amounts of movement on the graph or on the poset, right? You can't, I mean, the distance between 2 points can be at least 1 or a 0 or 1, right? But it can be more than that, but it's discrete anyway. So this is this is like the infinitesimal motion on the digraph will be moving 1 up. Okay, so I'm going to denote it by Hasse diagram. We're going to call it HP. Okay, and right now another construction I need to introduce is what is called the line digraph. So what is the line digraph? You take any digraph G. Any digraph G. So it has vertices V and edges E, right? And so I associate with it G hat. G hat is V hat, E hat, right? Where V hat is just E. Okay, and if I have two edges which are consecutive, so if so E hat is the following, best in the picture. If this is one edge, E, and this is a consecutive one, E prime, right? Then there's going to be a morphism from E to E prime. This is the indecomposable morphisms in, so the indecomposable edge, I'm jumping ahead a little bit, but these are going to be the edges of G hat, right? From E to E prime. So these are the edges. And sometimes I denote it like this. So this is the original graph, and that's the edge, E prime, or whatever you want to call it. Okay. So now, suppose that I did that to any digraph, or in particular, if I did that to the Hasse diagram of a poset. So suppose I do this to a Hasse diagram of a poset. So if HP is Hasse diagram for P, I can look, in particular, it's a digraph, so I can look at HP hat, right? So what's the point? Hasse diagram is basically a graph which is acyclic and transitively reduced. If you do a construction like the line digraph to an acyclic and transitively reduced digraph, you get, again, an acyclic and transitively reduced digraph. So this is acyclic and transitively reduced. All right. So in particular, it is the Hasse diagram for another poset. So it's an Hasse diagram for a poset P hat. What are the objects of P hat? The objects of P hat are the intercomposable edges in HP. Sorry, in P. Okay. The object are the intercomposable edges, so the edges of HP. So the objects are the edges of HP, not of P, of HP. Okay, and then the morphisms are the compositions of things like that. All right. In particular, I have two functors from P hat to P, phi and beta. Take an object to its source or to its target. Okay, so it's exactly the same idea as before, except now I also have morphisms. So these are now functors. It's not difficult to check that if you have, well, I can actually do that. So if you have like an edge, right? An edge E in P hat, that's an object, right? Then phi is going to take it. So that's going to be phi. We're going to take it to itself. And that's going to be beta. We're going to take it again to itself. Okay, let's call it A and B. So that's A and that's B. All right. And if you have two of them, so that's E prime, so that's C now, right? Then this goes by, so this one will be sent by beta to B and by phi to C. And so now, if you want to compose, basically, the morphism is going to take you from this edge to that edge. Okay, so you can compose morphisms. Sorry, it's going to take you, sorry, I goofed up here. So that's going to be the effect of beta, and that's going to be the effect of phi. All right? So you have two functors. Amazing. So what can you do? Exactly the same construction. So now you look at phi and beta, right? Phi and beta, right? I brought them here. These induce functors from KP mod to KP hat mod, which we can call phi star and beta star. As a result, I can now look at the Grothendieck group of isomorphism classes of KP modules or KP hat modules, right? And I get induced homomorphisms. So Grothendieck group of KP to Grothendieck group of KP hat. Oops, I forgot the Grothendieck. How can anybody forget Grothendieck? So it's bad practice. Right, I have these two homomorphisms now. It's less important to me at this point, but these actually are ring homomorphisms because these are rings with respect to tensor product over K. And I can define the gradient. I can define the gradient as the difference. The gradient is equal to phi star minus beta star. So we got through from graphs, right? From graphs to then categorifying the idea of a gradient on a graph, and then we categorify. We continue with the categorification, and now we can do this for KP modules. Okay. Okay. Let me see. Right. Okay. So maybe just to make things, I want to digress a little bit, and in case it's not completely clear, I want to look at an example of what an HP and an HP hat. So if I have HP, is going to be this. So something like that, right? Also, you want to do this in order to establish some sort of notation. So let's give them names 0, 1, 2, 3, 4, 5. And so what are the objects of HP hat? So this is going to be HP. Okay. What are going to be the objects of HP hat? These are the objects in red. Okay. And the morphisms between them are like this. So I'm going to copy that. So here is HP hat. And the names are 0, 1, 1, 2, 1, 3, 2, 4, and 3, 4, and 4, 5. Okay. All right. Good. So I have now a concept of a gradient. What do I do with it? Hmm? Find beta, go from P hat to P, right? Oh, so if you look at, also it's a good thing I gave this example. So if you're looking at HP hat over there, right? So the objects have the same object as the whole, all of, this is just the hash diagram for P hat, right? Right, so beta is going to take, I'm going to go from bottom to top, from left to right, okay? It's going to be 0, 1, 1, 2, 3, 4. And beta is going to be 1, sorry, phi is going to be 1, 2, 3, 4, 4, 5. And morphisms respectively, okay? Slower? Same question, yeah? Okay, so you have the white bit, the HP, and the red bit is the HP hat, right? And so the beta functor is going to take the objects denoted here by two numbers to the first one. So 0, 1 and 1, 2 and 3 and 4. So the first one, so the back. Okay, so this corresponds to the edge 0, 1, and beta is going to take it to 0. All right, etc. And the phi is going to take them to the front of that every edge. So 1, 2, 3, 4, 4, and 5. Okay. Any other question? It's obvious choices. There's no other chance. No. I had this picture over there. You can see it. This is simpler, right? But you see that you have the beta will give you a map from A to B, and phi is going to give you a map from B to C, and these are the same maps basically. These are the same maps as you have in P. Okay. Okay. So what is the first thing you do when you have a gradient? You ask what are the features? And one of the things you are asking is, what if the gradient is 0? When the function is 0, usually, not usually, always, when the function is constant. So all right, so that's very nice. Or rather, you start with a constant function, and you say if a function is constant, you compute a derivative. Derivative is always 0. Amazing. Not very difficult to prove. Almost equally easy is to, it's a little harder, not to be honest, but almost equally easy is to show that if your module is locally constant, in other words, if every morphism is taken by the module to an isomorphism, right? If every morphism is taken so locally constant M means that every morphism, M of every morphism, is iso. So this is not only for this particular context, any module over any category. So M from C to vector spaces or to any other category, if you wish, is locally constant if every morphism is taken by M to an equivalence in that category. Okay. So in our case, if M is locally constant, then it's not difficult to see that nabla of the class of M is equal to 0. Okay, because what you will have, if you look at this example over there, what you will have is two modules with isomorphisms everywhere. And it's not difficult to show that they are, that basically they are isomorphic. You can construct isomorphisms by choosing one and then completing the picture as required. All right, so that's encouraging, but it's not very much. So I want to now state a theorem, I'm going to call it theorem 1, which asks the question, what happens if the gradient is 0? Do you get a module which is locally constant? Now here I have to restrict a little bit the conditions. So, and remember that I want to look at things locally, right? So let's let P be finite. Let's let P be finite, and let's let T be a subgraph of its Hasse diagram, which is a tree. Okay, connected. I'm not writing connected because I'm going to ask for something else. Assume that T is a digraph. T hat is connected. So I didn't write that T is connected because this is implied by this. If the associated line digraph is connected, then the graph that gave rise to it is connected as well. So assume T hat is connected, okay? And now I can look at the sub PT, the sub poset of P, right? Which is generated by T. Generated by T, okay? I can look at MT, which is M restricted to PT, okay? And I want to assume that nabla of MT in the appropriate Rothendy group is equal to 0, okay? So, I mean, the situation could be that HP itself is a tree, in which case this applies to the entire poset, but it doesn't have to apply to the entire poset. As long as I have a tree whose a subtree of the Hasse diagram, whose line digraph is connected, I can localize to the subposet that it generates and the module to that subposet, and I want to say some things about that module, okay? So you're assuming that the gradient vanishes there, then the three things happen. Well, two things really. The third one follows immediately. So for every for every U and V in PT, there exists an isomorphism alpha UV from MU to MV such that alpha, I better not get confused here. Oh yes, alpha UU is the identity. That's not confusing. The identity on MU. And compositions work nicely. So alpha, that's the place where I should not get confused. VW UV. Alpha VW. Alpha UV should be alpha UW. Okay. This may look a little surprising, but remember that for this to be 0, I need to have an isomorphism between two functors, phi star and beta star. I need to have an isomorphism. This isomorphism is being used to generate these. So it's not that surprising. It also implies that alpha VU, alpha VW is alpha WV inverse by definition, basically, because I need this. Okay? So that's one thing. So in particular, it tells you that on the objects of PT, all the point values are the same, are all isomorphic. But it tells you a little more than that. So 2. So if U less than W and S less than T are in the composable relations, in P, right, which means they're basically edges. They correspond to edges in PT, sorry. Correspond to edges in T, right? Then alpha WT compose on M T U less than W is equal to M T S less than T composed on alpha US. All right, so not only the point modules are the same, but so the point vector spaces are the same, but their morphisms on the intercomposables are kind of conjugated. They're not really conjugation because it's not the same element, but both ways. But you can write, for instance, alpha WT M U less than W compose on alpha U S inverse is equal to MT of S less than T. So all the intercomposable bits of the poset get the same morphism. Okay, morally. So the same rank in particular. Okay. And of course, as a consequence, you get that M is not necessarily locally constant, but it is locally constant if and only if M U less than V is iso or some in the composable U less than V in T. M is not, MT is. Okay? That already tells you the situation is a little bit more interesting than it is in normal calculus. And indeed, to clarify this, I want to give some examples. So let's look at some examples. Example number 1 is the simplest one. I'm going to look at category poset with 2 objects, and I'm going to put K in one and K in the other. And I'm going to put the identity. So of course, this is locally constant. So if this is my M, or rather, I'm going to give it a name. I'm going to call it K bar, all right? K bar. then clearly nabla. Oh, no. Sorry. Take it back. I want to give it a better example, nicer example. Sorry. So take again the same. Take the same poset. The same poset with objects 0 and 1, and take any morphism between them. So anyone, right? The line diagram of this is just a single point. So this morphism gets forgotten completely. So nabla of this guy is going to be 0. Because all you're doing is just subtracting the corresponding vector spaces. Well, provided that M0 and M1 are abstractly isomorphic, not necessarily through A. Excuse me. That's better. Okay. Now, second example is P arbitrary. And K bar is basically K bar of any X is K. And K bar of any morphisms, X less than Y, is identity. So that's a locally constant module. It's a very simple locally constant module. Everything is identities. Then, of course, we know already that nabla of K bar is 0. All right. Cool. 3. So again, P arbitrary. And I'm going to look at K bar, K0 bar of X is K again. Okay. But K bar 0 of X less than Y is not identity, but the other obvious homomorphism of K, 0. So again, nabla is 0. Okay. Notice this does not contradict anything in the theorem, obviously, because all the theorem is telling you is that the morphisms on the indecomposables and on the indecomposable arrows are basically the same. Well, they are basically the same in both cases. Okay. But it does tell you that you don't get necessarily constant modules. You really don't. All right. And then the last example is slightly more involved, and I want to emphasize this. So, fourth example, consider the following: M is K squared, K squared, K squared, and I take 1, 0, and 0, 1. Okay. So I hope this is clear. So if K squared is generated by X and Y, this takes X to itself and Y to 0. This takes X to 0 and Y to itself. Okay. So I want to, I mean, you can actually compute the gradient directly. What you get is, basically the phi is going to look exactly like this, and the beta is going to look exactly like that. And of course, by switching the two coordinates, they're isomorphic. So the difference is 0. Okay. So that's good. So I know that the nabla of M is equal to 0. But I want to make another observation, and that is that, in fact, M is isomorphic. This is something that, in Introduction to Topological Data Analysis to Persistence Homology, this could be an example. So M is isomorphic to M01 plus M12, right? The two interval modules, where M01 is K with 1 and 0, and M, so that's M01, and M12 is the complement K with 0 and 1, okay? So M is isomorphic to the sum of these two, to the direct sum of these two. All right? And so nabla is additive. Nabla of M is equal to nabla of M01 plus nabla of M12. Either one of those is not 0, right? Either one of them is not 0, but their sum is 0 because they're equal to, one is the additive inverse of the other. Okay? So, yeah. So this also shows you, I mean, the reason to emphasize this particular example, because this also shows you that that basically, I mean, makes you suspect at least that if you have two modules of the same gradient, right, then it's not that like you're going to have the difference going to be a constant module. Okay? A locally constant module. So, yeah, one thing you could hope for is that if you have two modules, like in calculus, if you have two modules with the same gradient, then if you take their difference, that's going to be a module which is locally constant. Well, that's not the case, as you see from this example. Okay? But what can you say if, so that's the next question. What can you say in case, so if you have nabla of M is equal to nabla of N, what does that imply? Okay, this means in particular that M minus N, the classes of M minus N, is going to be in the kernel of nabla. Okay, so it's an object, it's an element of the gradient 0. So that also has an interesting answer. So this is theorem 2. So P is finite. P is finite, and nabla M equal nabla N. So nabla of X, where X is M minus N, is equal to 0. I want to define the rank invariant, the rank as, because they have this, no, sorry, it's not 0. That's 0. Yeah, that's better? Yeah, I thought so. Right, so I want to define the rank invariant as a homomorphism from the Grothendieck group on KP to the integer, to the, sorry, not the integers, but the functions from the morphisms in P to the integers. And that is defined by the rank of M applied to phi is basically the rank as a map of vector spaces of M phi. Okay, so that tells you in particular the dimension of every point module when phi is the identity, and the rank of everything else as well. So the first statement here is that if U0 U0, U1 is less than V0, V1 in P hat, sorry, in P hat, then the rank of X, of U less than V, U0 less than V0. So this guy less than this guy, not inside, this less than this, is the same as the rank X of U1 less than V1. Okay. Now, so that's in general without any further restrictions. Now, if T in HP is a tree such that T hat is connected, then two things happen. Then the rank of X, so this is X restricted to tau, to T, the rank of X restricted to T of N is constant on identity morphism. Which in particular tells you that for every object, M of X, say, M of X is isomorphic as a vector space to N of X. Okay, and furthermore, and so I call this, I call this nothing. And then also the rank of xt is constant on all in the composable relations. All in the composable relations. In P. In T, sorry. In PT. Okay. Okay. So the rank invariant is actually a very commonly used thing in representation theory, particularly in topological data analysis. It is known not to be a complete classifier, but you could try to compare it to the gradient and ask yourself, well, are they comparable? And it turns out that they are not comparable. In other words, there are things that where the rank invariant performs better than the gradient and vice versa. All right, so let me give you some examples. So I want to look at M1, which is going to be K squared, K squared, K squared. And M2, which is going to be also K squared, K squared, K squared. But M1 is going to be the previous one. So it's going to be 1, 0, and 0, 1. And M2 is going to be 1, 0, and 1, 0. Okay, so so the gradient of M1 is equal to the gradient of M2 is equal to 0. This one I showed you, and this one is well, that's easy because they're exactly the same, right? But the rank of M1 is not the rank of M2 because the rank here from beginning to end is 0. The rank here from beginning to end is 1. Okay, that's an easy example. Another one to show you the opposite. So in other words, the rank invariant is performing better here than the gradient. Another example, I need a bit more space. So I'm going to write here M alpha. So this is one of these tame examples. So you have K squared with 4 objects here, K, 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 and K. You have 0 here and 0 here. And you ask, where is the alpha? So I want all of these to be rank 1, right? The rank here and here is clear because they're zeros. So all of these are rank 1. The alpha is basically, there is a 1-parameter family in K that classifies all of them. Okay, so it's an infinite family of non-isomorphic indecomposable modules. Okay, and so it turns out that nabla of M alpha is equal to nabla of M beta if and only if alpha is equal to beta. In other words, it distinguishes them completely. Okay, where the rank invariant is always the same, right? Okay, I have about 1 minute to go. And if you, I mean, there's a paper about this in the archive. I just wanted to use this 1 minute and maybe 1 minute more to tell you a little bit about, what else goes into this. So we do have a concept of divergence. Okay, divergence in graph theory is defined if you're looking at functions into the real or complex numbers, is defined by the fact that these are inner product spaces, and the divergence is defined as an adjoint with respect to the inner product space, the inner product of the gradient. And then the composition gives you Laplacian, and then you can define higher Laplacians by generalizing this concept. There's a very good survey paper by Lim that you can find that tells you everything that you need to know about Hodge theory, basically for graphs, for digraphs, or for graphs in general. When you look at this kind of setup for modules, you immediately see a problem. So, I mean, first of all, there's no good concept of an inner product. I mean, it's something like inner product that is going on in representation theory of quivers, but it doesn't quite correspond. You think it doesn't quite correspond to what you see in real valued functions. So, but you need a jointness. So the obvious thing that you can do, I mean, these two functors, phi star and beta star, have left and right adjoints given by the so-called left and right Kahn extensions. So these, if you look at inner product given by the dimension of the hom over Kp from M to N, right? Or you can look at the X over Kp from M to N and take its Euler characteristic, which is something that is done actually in representation theory of quivers. These two things actually function sort of like an inner product. And if you look at the first one I mentioned, the dimension of the hom, then you actually do get this adjointness and you can define divergence, except you have right divergence and left divergence because you have both a right and left adjoint. Okay. Then you ask yourself, okay, why does that make sense? You go back to graph theory, look at the setup that I started with, and it turns out that the left and right Kahn extensions are isomorphic, in which case they actually are the adjoint. So the usual concept fits exactly. The problem is that this is a non-commutative theory, whereas when you just look at numbers, it's like basically moving from numbers from R to matrices over R. It's not commutative anymore. So you need to think about left and right. So you can define divergence, you can define Laplacian, and you can generalize it further, which is now a work in progress, to higher Laplacians and higher operators and higher Laplacians and all the rest of it. So I guess I have to stop here. Thank you very much.
Thank you. Any questions?
Carlo.
Thanks for your talk. And you gave a lot of examples where this Laplacian vanishes.
Sorry?
You gave a lot of examples where this nabla vanishes. The gradient vanishes.
Yeah.
Are there simple examples where you can compute it and it does not?
Oh yeah, of course. Of course. Yeah. I mean, if you took
Can you
look
give
at
us one?
I did give you an example where it doesn't. These two.
Okay, I missed it. Okay,
right?
because the
I mean,
sum.
one is going to give you a 1, kk and a 1. One is going to give you kk and a 0.
Okay, the sum vanishes, but each one it does not.
Yeah, I mean, most of the time it doesn't vanish.
Okay. Was a stupid question.
No, there's no such thing as a stupid question. But I mean, yeah, I mean, the whole idea of this is to say, okay, what can I do next? I can look at the gradient, right? And I can think of, where does this module grow? In which direction does it grow? I can think about defining, take a path through a point and think about the behavior, the kind of the linear behavior of the gradient on this path, which is very easy to compute, right? And by checking all the path going through a point, I can say, like, I can look at direction of, maximal growth or minimal growth or whatever. So you can think about applications for things like gradient descent, in various applications. So, I mean, this thing could be very applicable, but unfortunately, I have my heart is pure. So I think, first of all, the theory. Yes. Yeah, because if you do, you don't have to, but life is going to be a lot more complicated if you don't. So basically, if it's not a tree, then you have to make sure that things fit together exactly when you close a loop. Or otherwise, it's basically an integrability problem. So if you don't do that, if you don't assume that it's a tree, then you get in trouble because things just behave differently if you take different directions to get from.
Okay, more questions? Okay, if that's not the case, let's thank Ran again. Hey, welcome back. So the final talk of today is the talk by So Yamagata. He's from Fukuoka University, and he's going to talk about mapping fiber graphs in naive discrete homotopy theory.
Okay, so to begin with, thank you very much for. I'd like to thank to the organizer for accepting me to give a talk at such a great, interesting conference. And actually, this is the third time to come to Pisa, but Pisa is a very beautiful city, and I was really looking forward to coming here again. So I thank you. And so today I'd like to talk about the mapping fiber graphs in naive discrete homotopy theory. But mainly I wanted to not talk about mainly my talk results, but recent developments of this theory. And to begin with, before going to my talking, for some reasons, there is no abstract on website of the conference. Maybe I thought I sent the abstract with titles, but no abstract on the website. So, so here is the abstract on my phone. So recently, it is really active to import the idea of homotopy theory to discrete or combinatorial structure, such as graphs, simplicial complexes, or metric spaces. So here I wrote finite, but in my this discrete homotopy theory is not focused on not only finite but general metric spaces. Okay, so the discrete homotopy theory, especially I will talk about the what is called an A-homotopy theory, which is a homotopy theory defined on originally simplicial complexes. But later, for some technical reason, it comes down to a theory of graph, homotopy theory of graphs, or metric spaces, which has recently really developed by Kranzer and Kapurkin and others. And this is not only interesting in itself, but also it has some applications to not only combinatorics, such as matroids or graph theory, but also the topology of especially subspace arrangements, which is my original motivation, such as the k-pioneers of some subspace arrangements, and recently to like a more application TDA. So in this talk, I will introduce recent developments in homotopy theory, including some and some results of the speaker of my result. Okay, so let me explain the overview of the homotopy theory. So what is discrete homotopy theory? So for topological spaces X and Y, the central notion is a homotopy, which is a continuous map. defined on x times interval 2y. So we want to mimic this notion. So especially discrete homotopy theory defined on graphs or simplicial complexes or metric spaces. So we need to change these objects and so on. So first, what is the interval 0, 1 in graph theory? We adopt a line graph, which I will define later. And also we need to define what is this product. We adopt here Cartesian product of graphs. And this product is also called a Cartesian product, the same notion. And finally, what is the continuous map in graph theory? We adopt a graph map. Then we can define a homotopy between two graph maps. And before going the technical details, let me explain the original construction. So originally, the work goes back to the Adkins work, who is a physicist and who modeled a variety of social technological networks using simplicial complexes. But so we have a simplicial complex, but the theory comes down to the graph theory as following. So let K be a simplicial complex. Then we can associate a graph as following. We define a Q connectivity graph, gamma QK, which is a graph as the vertices corresponds to the maximum simplices of dimension greater or equal than Q. Then two vertices sigma and tau are adjacent if they share a Q face, so Q dimensional face. So this is example. So consider this simplicial complex. So 5 triangles. Then gamma 0, K is like this, so just a complete graph. And gamma 1, K is like this cyclic graph, because we have 5 vertices corresponding to each face. And each face has one dimensional edge as intersection. So we connect these two vertices. Then we get this kind of cyclic graph. And gamma 2, K, is just a discrete graph. So the starting point is simplicial complex, but the theory can be, so it is sufficient to consider only graphs. So later we focus only on graph category. Then anyway, we can define graph. Then the discrete homotopy group, which we define later, can be defined. Okay, so this is the overview, and this is a summary on recent developments on discrete homotopy theory. So the origin is this Atkins work, and then the theory was formalized by Kramer and et al., Barcelo, and so on. And they defined the homotopy groups of simplicial complexes. Then the construction was cubicalized by Babson, Barcelo, et al., and using a cubical technique, and they defined the homotopy groups of graphs. Then the theory was generalized to metric spaces. And there's also analogous of homology theory. So here not discrete homotopy, but discrete homology theory also defined this year. And then Babson and Barcelo et al., they studied some basic properties of the discrete homology or discrete homotopy groups. Then more recently, Krantz and Kapulkin categorified the theory, and now they actively study the theory, like on the model structure of the graph category, or covering spaces and classification theorem. And now now they are working on weak discrete homotopy theory and so on. So this is really recent work. Okay. So now let me define discrete homotopy. So first, let G and H be graphs. Then we define a Cartesian product of graphs as following. So the vertex set is just a Cartesian product of vertices. And for two vertices, V1, W1, V2, W2, these two vertices are connected by an edge if V1 equals V2 and W1 and W2 is in edge of H or vice versa. So this is example. So if we take triangle and line graph, then the Cartesian product graph is like this. So this is the definition of Cartesian product of graphs. And now we define a graph map. So let G, H be graphs. A graph map F from G to H is just a set map on vertex set such that V1, V2 is edge of G, then the image is vanish or the edge of the image graph. Now, then we can define a homotopy between two graph maps F and G as following. So consider two graph maps F, G. They are a homotopic if there exists an integer m and the graph map G tensor IM to H such that F0 is F and F M equals G. Then we call these two graph maps a homotopic, and this gives actually gives an equivalence relation. And analogously, we can also define a relative version of this A homotopy. So let G and A be graphs such that A is a subgraph of G. Then we call the GA a pair. Then we can define a homotopy between pairs. So a relative graph map FGA HB. So this definition is really the same as geometric one. So it's a map FG to A with the restriction to A goes to B. Then we can define a relative homotopy like this. So if these two maps F and G are relatively a homotopic, if there exists an non-negative integer m and the graph map G with this property. So really just a mimic of geometric homotopy. Now, then we can define a homotopy groups of G. So let n be a non-negative integer and V0 be a base vertex of the graph. Then the a homotopy group of G at V0 is defined as this set. So here, I infinity is just a line graph. So each vertex is so it's kind the shape is isomorphic to the set of integers. So vertex and just a line shape edges. And take its n tensor. So this is the I infinite tensor n. So for example, if n equals 2, the graph is like this picture. And for this kind of graph, we define its subgraph I bigger than m tensor n. This is a subgraph of this graph, such that so minus m consists of the vertices of minus less than m minus m and bigger than m. So we remove the inside vertices and edges. So this is the graph I bigger than m. Then so we define the outside of vertices goes to V0. So okay. Then we can define a homotopy group. So this is the definition of a homotopy group of graphs. So let's see an example of. So let's see example. So this is a triangle graph. Then consider a graph map like this F. Then this map F can be contracted because we consider this contraction. So So orange, at once we contract orange and red vertex to blue vertex. So in general, for this graph, the A1, so let's say discrete fundamental group vanishes. Of course, not that. If you think this just geometric one, this should be fundamental group, should be Z. So this is different. But anyway, so in combinatorial point of view, this graph is a contractible space. And square is also the same. So in this case, we consider first green to blue and contracting red vertex to orange. First step. And then second step, orange to contract orange vertex to blue. Then we can also contract this graph to a point. So in combinatorial point of view, in this sense, the square graph is also a contractible space. Again, in geometric point of view, this should be Z. So different. But but by an easy exercise, we can show that more than 5 vertices. Then this cannot contractible to a point. So in this case, the discrete fundamental group has Z. And so there's a slogan in homotopy theory people saying that A1 measures not geometric, but somehow kind of combinatorial holes. But this is, so in some sense, this seems to be only a kind of combinatorial invariant. But there's also there's also geometric model for the theory. So this is classical result for given graph G. Then define a space XG as following. So let's see this graph as example. First, we see this graph as a topological space. Then just a cell complex. Then we attach 2 cells to 3 cycles, all 3 cycles and 4 cycles along the side. So then we define such a complex as XG. Then its geometric fundamental group is isomorphic to the A1 graph, A1 group of the G. So in some sense, this graph, this XG is a kind of geometric model of this graph. So this is just a classical result. And of course, we want to expect the higher version, but it was really long time conjectured. But 2 years ago, Krantz and Babson et al. They conjectured, but to prove this theorem, they assumed like a kind of cubical version of simplicial approximation property, which is still an open problem. But Krantz and Kapurkin, they avoid assuming such a property, but using somehow cubical homotopy theory. Then they showed this isomorphism. So for graph G, here I don't explain more, but associate a cubical complex XT. This is different space from this space. But anyway, they define a kind of cubical complex XG. Then this isomorphism holds. So this XG is somehow a geometric model of this homotopy groups. But the problem is, of course, what is this complex? So this is the problem for now. But anyway, so this is not only combinatorial invariance, but also can be seen as a geometric invariant. And it has some applications. For example, a graph G is a basis. So there's a statement saying that a graph G is a basis graph of a matrix. If I don't leave some conditions, and the last condition can be translated to the A1 group. Levi tried homological approaches, or for application, time series analysis of data, or geometric group theory, and so on. So there are many known applications. But also, there's also another application to subspace arrangement, which is my original motivation for working on this theory. So let W be a Coxeter group, and A be a Coxeter group of type A, so symmetric group. Then, of course, we can define a braid arrangement. And the braid arrangement consists of hyperplane of this form. And of course, the complement is K pi 1. And the fundamental group of the complement also known. And as its generalization, we change A to general Coxeter complex, Coxeter group, then also the similar result holds. But there's another way to generalize this object. Not only xi equals xj, but also xi xj equals xk. So one more equality here. Then such an arrangement is called not, in this case, not hyperplane, but a subspace. So such an arrangement is called, in particular, this is called 3 equal subspace arrangement. And this complement is also known. And of course, we can also generalize A to W. And so on. So in this direction, we can change not only 3, but general K. Then the following theorem holds. So this ANKRW is a generalization of 3 equal subspace arrangement. Then, at least fundamental group level, okay, so let's see that will be a Coxeter complex. So which is a Simplicial complex associated to Coxeter group. And its associated connectivity graphs. Then it's some dimensional connectivity graph of Coxeter complex. Its A1 is isomorphic to geometric object, which is a K parabolic subspace arrangement. And this, so this is shown by Barcelo et al. But the higher dimensional case is still now it's open problem. But but the Carranza and Kaplukin work, so 2 years ago, they gave a key fact. And so this corollary is not a corollary of this theorem, but a corollary of their work. As a corollary, we can say that let x gamma n minus k plus 1 CW, so connectivity graph of Coxeter complex. So this is a cubical complex associated to this graph. Then, so this holds. And the left one is the same. So finally, if we can connect these two spaces, so here, not only here now, no combinatorics, but geometric and homotopy theory. So if we can find some relation between this subspace and this mysterious cubical complex. So for example, they are homotopy equivalent, or even weak homotopy equivalent. Then this isomorphism holds. So so that's why I'm trying on this complex and this theory. And recently, I and Liu, who is now my friend in China, we are conjecturing first the case W equals A and K equals N plus 1. Then we are now trying to prove, but anyway, so still conjecture saying that in this first step, we have, if this cubical complex is homotopy equivalent to the n minus 1 dimensional sphere, then then these two spaces are homotopy equivalent. So we can check this isomorphism. But now we have no idea to prove how to prove this homotopy equivalence for now. But anyway, so this is a conjecture. Okay. So to try such a problem, we need to know what is discrete homotopy theory. So so the last section is just one of my trial to understand this theory, and which includes not interesting result. Okay. So I defined a mapping fiber of mapping fiber graph. So let F be a pointed graph, then as a mimic of classical homotopy theory, we define a mapping fiber graph, right, which is defined as a pointed graph on the vertex set of this. So this is just mimic of classical definition. So yeah, but so first my motivation is to give a puppet sequence. So to construct a fiber sequence and as a corollary to give a puppet sequence. So actually, just for digraph version, puppet sequence is yielded by Yao and et al. So I wanted to give such a result, but these theorems obstacles to do it. So let F be a pointed graph map, and MF here, and this MF to Y defined by X omega to omega M, so the endpoint. Then if this phi exists, then this F should be 0 map. And so if I don't, if I don't leave, so such a map phi from X to MF exists. If I don't leave, this map F is a trivial map. So so for all vertex 2 goes to the one base vertex. So very trivial result. And as a corollary of this theorem, we can show that for any z, this homotopy set should be 0. So this mapping fiber graph is what I constructed is very uninteresting object. But I think so. I think because to be a map is graph map is a kind of strict, strong condition. So so this is one of the circumstance evidence why we have to not naive discrete homotopy, which is a quotient category graphs by a homotopy, but weak A homotopy. So this is important. So weak A homotopy and A homotopy are really totally different one. And here we are assuming strict A homotopy. So we have to work not on A, but weak A homotopy. But it is now under constructing and very difficult problem. So, and this is the final slide. So anyway, I wanted to seek more applications of this discrete homotopy theory. And to explore more applications, we need to detect what is XG. For example, how to detect the homotopy type of XG. This is actually infinite dimensional, but if you consider retroaction, then I think it should be finite dimensional cerebral complex. But how to determine its homotopy type? And also, is it possible to construct Eilenberg-Maxwell spaces? This is also a problem. If so, how to do it? And explicit computation is also interesting. For example, A4 bounded A5 tensor 3 is isomorphic to Z over 2. This is corresponds to the homotopy group of sphere. So this analogy to this isomorphism. And or does homotopy excision property hold for all or specific graphs? This is also not known. So there are anyway many open problems, and step by step it's developing. Okay. Okay, so it's okay. So I will stop here and thank you very much, and let's enjoy lunch. Thank you.
Thank you very much. Questions?
Just a clarification about the part on Coxeter groups. Was that about all Coxeter groups or just finite ones?
You mean this?
Yeah.
Just finite one.
Okay,
Yes.
thank you.
Thank you for your talk. If you said construct Eilenberg-MacLane spaces, do you mean in the ordinary sense, or for A theory?
You mean
the third point?
This?
Yes.
Yes. I'm assuming A theory here. Yes.
The A theory. So
theory.
you want space graphs that have
you mean here I mean weak A homotopy. Yes.
Sorry.
Weak one. So
the
geometric. I want to construct an Eilenberg-MacLane graph up to weak A homotopy. Yes. Because A homotopy is triangle and the square has not homotopy equivalent. So yeah.
So I'm not sure I understand. So your graph will have what property exactly? What will make it an Eilenberg-MacLane graph?
N homotopy group has group G and others one vanished. So this similar one, but yes, similar to the classical Eilenberg-MacLane space. But that such a graph should be uniquely exists up to weak wave homotopy. Yes. Yes.
More questions? If this seems not to be the case, let's thank the speaker again.